All right. So as we were having the chat on the site here, I would rather say good morning, good afternoon, and good evening for everyone in the class because I pretty much trust that we have different timelines that we are going through right now. Um, so before we start, my name is Mohammed Yusuf, and I'm an AWS technical trainer. I've been with AWS for the past 4 years. And I've been in the training for the past 17 years of my life. And before we actually move further, I would appreciate that if you're not using the microphone, that you put yourself on mute so that we don't get a feedback. That'll be truly appreciated. Thank you very much. All right, so let me just bring up my camera. I'm going to be with you for the next hour. We may, depending on how the class actually runs or how the session actually runs, we may cross the 1 hour barrier a little bit. But we'll see. I'll try to restrict myself to be within 1 hour timing, talking about the AWS networking and in particular about the VPC, breaking it down, understanding what it is, why we need a VPC, how do we build a VPC, and the different components that forms up a VPC, and then eventually we will close that with a demo and a final step of what to look at next. So the session will be formed up of 3 parts: a theory part, a whiteboarding board, and a practical demo. And the whiteboarding and the practical demo will be sort of a recap of what we're going to discuss from a theory perspective. And it's also going to be going side by side. So we'll be doing the drawing and then we're going to execute that on the actual environment. Then go back to the drawing, add one more component, and then go back to the environment and add that so that you know where every single piece of the different VPC components are actually going to fit. Absolutely, we're not going to cover 100% of what you need to know about VPCs, but we are surely going to cover some important aspects that should get you started building your own VPC and understanding what it is and how it can be useful. All right, so without any further delay, let's get into it. The day's agenda is basically from an architectural perspective, we need to understand why do we need a VPC? And the main answer to that question is going to be throughout the material that we're going to cover, which is basically a network. A VPC is a network, and it's an abbreviation of Amazon Virtual Private Cloud. So it's going to be your virtual network inside AWS, and it's going to be the location into where we are going to deploy our resources. These resources are mainly in the form of an EC2 instance, right? So what is a virtual VPC? What are subnets and what are the gateways and their uses, as well as how we can control traffic traveling between different parts of your system, between different servers that you have deployed into that VPC. All right, I'm going to turn off my camera right now to conserve bandwidth and give you more focus on the slides itself. So let's get into it. So Amazon Virtual Private Cloud, what is it? As we said, it's a private network space that isolates you as a customer when you are building something on top of the AWS platform. You need your own virtual network, a network that you cannot reach from to any other network, and no other network for any other AWS customer can reach into your network unless you explicitly want this to happen, right? So the first thing is I need a network. It's going to be like let's just use an analogy of a school here. So we need to build a school. This is going to be our school. Um, Again, can you please put yourself on mute if you're not using the microphone? Thank you very much. All right. So that school is going to have all of our resources. In other words, it's going to have all of our servers, which we call EC2 instances within AWS. So it provides you with the logical isolation that you're looking for from any other virtual network owned by any other AWS customer running on top of our infrastructure. And then it allows you to control how you are going to allow traffic in or out of that network. So it's exactly what you were doing in an on-premises data center. If you have an on-premises data center or working for a company that owns its own data center, they need a network. So in order to build that network, they buy hardware stuff. They buy routers, they buy switches, they buy servers, and then they wire them up in a way that allows certain level of communication between these resources. Now we're going to be doing exactly the same inside AWS, but it's going to be from a virtual perspective. So there's no physical connectivity or no wiring that is going to take place. Everything is going to be an overlay virtual network that we actually build and deploy using software. And the software that we're going to use for that is going to be the AWS Management Console. Now, there are alternatives to that, of course. You can actually do it in other ways, but the preferred way that we're going to use today is the Management Console so that everybody knows where things actually fit. All right. So a VPC is your virtual network. It's dedicated to you within your AWS account, and you can actually build it using an IB version 4 IB addresses, or optionally using an IB version 6. Now, we all know that one way or another, we will end up being building VPCs using IB version 6 one day when we completely run out of IB version 4 IB addresses that are available. But the perspective that we're talking about today is not really focusing on routable real IB addresses on the internet, rather than actually focusing on private IB addresses within your VPC. And that's what we are trying to achieve, is to have a private network where our resources can communicate internally. Of course, at a later point, we are actually going to take those resources out and allow some of these resources, but not all of them, the capability to communicate with the internet and the internet to be able to communicate with them. Now, to create a VPC, you need to pick up a CIDR block, a classless interdomain routing IB address range, and then build your network according to that IB address range. I'll explain the details of this in a moment. Now, using that range, we're going to have a certain number of IBs available within our VPCs that we can allocate to our resources, to our servers that are running there. So when a server comes up on that network, it will grab one of those IB addresses and use it to communicate with other servers within the same network. And then we'll talk about how you can restrict access to those resources. Some of them are going to be private. You cannot communicate with them from the internet, and they cannot communicate directly to the internet, or even with some of resources that you have inside the VPC. We can also restrict access between resources residing within the same VPC. So that's also one more thing that you might be interested in doing. Okay, so now you probably know, and it's public information, that we have, well, as many AWS regions across the globe. So we have around 26 regions as of today, with more regions being announced over time. Now, a region, you can think about it as a physical location within a country, right? That region consists of availability zones. Those availability zones are again physical locations within those countries that are spread across a geographic area. The purpose of building a region out of multiple availability zones is that we can use these availability zones to implement failover in case if it's required. So we can build highly available solutions that runs across multiple availability zones within the same region. So if one of those availability zones goes down, along with all of the data centers that forms it up, we can actually redirect the traffic to another availability zone within the same region. All right. So think about it like that. If we take Bahrain as an example, this is where I actually reside, and we do have an AWS region here that consists of 3 availability zones. Well, I can build my solution to have an exact replica of itself across two different availability zones, place a load balancer in front of them, and if one zone goes down, taking down with it all the resources that I have there, the traffic will be routed to the other availability zone. Now, how does that fit within the schema of a VPC? Now, there is an important rule that we need to keep in mind. Whenever you create a VPC is region bound. So when you create a VPC, it lives within one region and one region only. VPCs cannot span multiple AWS regions. One VPC, one region. But in one region, we can have multiple VPCs. We can actually have up to 5 VPCs per region. And that's merely a soft limit. You can actually increase the number of VPCs per region if you make a support request to the AWS team. But let's just take the 5 VPC as our limit right now. When you create an AWS account, the AWS account gives you access to global AWS regions. You can actually switch your region from one region to the other at any time you want. So you can build a couple of VPCs in one region and maybe 2, 3 VPCs in another region, maybe 5 VPCs in another region, depending on how you want to lay out your network. So the purpose of the region here is it's representing the infrastructure into which we are going to deploy our network. And the VPC is that logical isolated network within that particular region. You can have one and you can have more if you want to. All right. So as you see here on the slide, in US West 1, for example, we do have 5 VPC regions 5 VPCs in that region. And in US East 2, we actually have 2 VPCs in that region. So depending on how you want to build your network, this might differ. Now, in our case, we are actually going to build one VPC in one region so that we can see how it actually works. And the process of building a VPC from there on is just a replica of what we're going to do step by step together. All right, so maybe I don't know a lot about IP addressing. So how does that work? Now, whenever you plan to build a VPC, you need to pick up an IP address range. Now, that IP address range is a private IP address range that allows you to, well, sort of reserve those IPs for yourself, those private IPs for yourself. So I may build a network as large as, I don't know, 256 IP addresses, and I may build a network that is as large as 1024 IP addresses, and I may build a network as large as up 65,536 IP addresses. And actually, that's the maximum size for an IP address range you can book for a VPC. So again, it depends on your actual need, how much or how many pieces of resources you actually want to deploy into that network. Depending on that, you're going to create a large network, medium network, or a smaller network, depending on your requirement. Okay, so as you can see down here, that's an example of an IP address range that we can pick up for our VPC, which is going to be 10.0.0.0/16. And I like to split this IP address range or CIDR block into 2 pieces. The left piece you can see here, and the right piece you can see here. Now, the left piece you can see on the left side, this represents the starting IP address you're going to have. And this is going to be 10.0.0.0. So that's the first IP address you can have within that network. And then it will keep growing, like 10.0.0.1, 10.0.0.2, 10.0.0.3, and so on. And the right side is the slash notation. This is what basically tells you out of those 4 octets you see here, that's each number you see on that IP address is actually a representation of an octet that is represented by 8 bits. Now, if I say /16, it means the first 8 bits on the right side and the second 8 bits on the right side are going to be used for hosts, while the 2 octets on the left side are going to be locked. This is what tells me that. It tells me the network octets that I'm going to use. All right. And I've got 8 here. That's 8. And I've got 8 here. So I've got 16 bits that are going to be locked. They are not going to change no matter what you do within that network. Every single instance that you will run within that network will have 10.0 at the beginning. The 2 octets that will change, however, are the remaining one out of the 32 bits that we have for an IP address version 4, which means the next 8, this one and that one. So this is going to be like 01, 02, 03, 04, until we reach the maximum of 256 for the 0 you see here, and then we switch to 1 on the next. So it's going to be 1 0, 1 1, 1 2, 1 3. Well, I found that it's best represented by that table. So imagine that we create a VPC that has this CIDR, 10.10.0.0/16, or anything else, doesn't really matter. Now, in our case here, we are going to have an IP address range of 65,536, I believe. So that's the amount of IP addresses we can have within that network. Now, if we start slicing that network into smaller networks, which we call subnets, as we're going to see next on the coming few slides, and each of those small subnets within that network are going to consist of 256 IP addresses. That means my first subnet is going to start with that IP, 10.10.0.0, then 10.10.0.1. And then it keeps going up until we reach the last IP address in that small subnet, which is going to be 10.10.0.255. But didn't you say 256? Yes, they are 256 because we are starting the numbering from 0. So that's a total of 256 IP addresses for that subnet. The next subnet is going to start at 10.10.1.0, and then it will keep going up, .0, .1, .2, .3, 4, until we reach .1, .255, and that is going to give us 256 IP addresses more. And then we keep slicing that large network that consists of this number of IP addresses into multiple smaller subnets, each of which contains 256 IP addresses, until we reach the max IP address that we can get to, which is 10.10.255.255. And that's the last IP address that is usable within that VPC. So imagine that we have a large cake, and then we take that large cake and then we slice it into smaller pieces. Each of those pieces is actually going to be 256 IP addresses out of the overall, cake, if you want to call it like that. All right. So now if you look at the CIDR examples, and those that we commonly use when we talk about networking within an AWS VPC, on the right side section here, we can have between /28 as a CIDR notation and a /16. We already know that /16 gives us 65,536 IP addresses. But if you go /17, that is going to half that number. So it's going to be 32,000 plus IP addresses you can have within that VPC. Now, what if I pick my VPC CIDR block to be /18? That gives you up to 16,000 IP addresses that can be used within that VPC. And every time you go up on the CIDR notation, you increase decrease the number of IP addresses that you can actually have within that VPC until you reach /28. That's the highest number you can have and the smallest network you can actually build within AWS. All right. Now, whenever you see us saying 0.0.0.0/0, it means all IP addresses. So, for example, one of the things that we'll be talking about is routing tables. When I say in a routing table that 0.0.0.0/0 can communicate with the internet, it means all IP addresses within the network in which this particular routing table is being used can communicate with the internet without any kind of pick and choose option. All the IPs there are capable of communicating with the internet. Now, what if I want to allow a particular IP communication with the internet? I can actually do that by saying, what's the IP address? And then using slash notation of 32. That references the same IP. It means I want to allow only this IP address, that kind of communication. Now, what if I want to allow a range, but it's not all the IPs? It's just a small subset of that range, like maybe a small subnet that has 256 IP addresses. So I can actually say 10.22.33.0/24. Remember, this is 8, this is 8, this is 8. That's total of 24. So it means I'm going to accept anything that has .0 until 255 being able to communicate with the internet. And being able to communicate with the internet is just an example. Maybe it's just being able to communicate with another network. All right. And then finally, what /16 means, it means that those two octets are changeable, which gives us the range of the 65,536 IP addresses. You don't really have to memorize these numbers, but you rather have to remember how they're actually formed and what the use of their mechanism of working. I'll be using some of these numbers as I actually go through my demo. All right, so again, back to the cake example. Now, this is a network, and this network is actually going to be, for some reason, it's not updating. Let me just discard the drawing that I've done. And let me reshare that again. All right, so that's a network, but instead of actually going for /16, we decided to go /22. And /22 is actually going to give us a total of 1,024 IP addresses. If you remember in the previous slide, well, /20 was going to give us 4,096. So /21 is going to give us 2,048. So /22 is going to give us 1,024, right? So the same rule that we applied before. So in that case, we went /22. So the whole VPC, the whole school, can have up to 1,000 students. Great. Now, if we started to break that large VPC into smaller subnets, or if we use the analogy of the school again, break the school into smaller classes, then each class can have, in that case, about 256 IP addresses. So we can actually create 4 subnets in that network, each of which can have 256 IP addresses. Or we can have 8 subnets, each of which can have 128 IP addresses. Or we can have 16 subnets, each of which is going to have 64 IP addresses. Now, it really doesn't concern me how you want to break out your subnets. You are bound by the maximum number available for the VPC, but you can break them inside the way you like. You can create subnets that are larger than others. You can create multiple subnets that are equal in size, depending on what exactly you are trying to achieve. The thing is, for this example, we broke this into 4 subnets, each of which is actually 256 IP addresses. For some reason, this is not actually appearing, so I'm going to write this down. It's going to be 251 here. So now you're saying 256 IP addresses, but we're actually seeing 251 IP addresses on the screen. So why there is a conflict? Well, there's actually no conflict. AWS reserves 5 IP addresses for itself out of each network that you create on top of their infrastructure. All right. So now we know that we can have a VPC. We can break that VPC into multiple smaller subnets. And we also know that the AWS is actually going to book 5 IP addresses out of each subnet that you create. Now, those IP addresses, the first one and the last one, are normally going to be blocked from pretty much any network. If you build that network physically, you cannot use the first IP address and the last IP address. Those are actually being used to connect the network locally, and the last IP address is actually used for domain broadcast. So instances or resources running within that network can actually talk to each other through that broadcast IP address of that network. And then there are additional 3 IP addresses, one for the router, one for the DNS server of that VPC, and one booked for future experimentation. So the first 4 and the last IP addresses are not going to be usable. You cannot actually use them to assign IP addresses to running resources within those subnets. Now, whenever you create subnets within the same network, the CIDR of those subnets cannot actually overlap, because if they can overlap, you can spin up a server that has X IP address on one subnet and have X IP address on another subnet. Now, that is not allowed. If they try to communicate, they won't be able to, and one of them is going to kick out the other of the network. So CIDR blocks cannot overlap within a VPC. Now, and within the subnets of those VPCs. Now, the subnet actually resides in an availability zone. So whenever you create a VPC, it stretches itself across all of the availability zones within that region. And then when you slice it down to smaller subnets, you have to match those subnets with the availability zones that you pick up. I'm going to show you this in a few minutes, so don't worry, you're going to see that practically. Now, again, just like a region can have multiple VPCs, an availability zone can actually have multiple subnets if you want to. Now, how do you direct traffic between resources within your VPC? Whenever you create your VPC is actually going to have what we call a default main route table. And that route table is only going to have one single route, the CIDR block of the VPC as the destination, and the target is going to be local. What this route in this routing table means, it basically means if we have 4 subnets, if we have 8 subnets, if we have 10 subnets, if we have 20 subnets within that VPC, any resources inside them are going to inherit that routing table on the subnet level. And so they can all talk to each other, communicate with each other using this route. From a networking perspective, all instances running across all of your subnets can communicate together with no restriction. Well, when security part comes up, we will learn how to control that kind of traffic. But for the moment, from a networking perspective, pardon me, and if we don't create our own custom route tables, well, and just get on with this default route table, it means that all instances running across all of our subnets can communicate together. In which, in a production environment, it might not be the case. We might not actually want to do that. We may want to restrict certain resources internally from communicating to other resources that we have internally. And this is where security comes into play. Now, typically, you should use custom route tables. And I'll also teach you how we can create custom route tables as well, so that we can control the traffic of each subnet as needed. All right. So looking at those subnets, is there anything extra we need to know about them? Well, you might often hear the word public subnet and private subnet. And public subnets and private subnets at the beginning, when we create a VPC and when we slice it into multiple subnets, they're all going to be private subnets, to be honest. Your VPC cannot communicate with the outside world unless you explicitly indicate that. So all of the subnets that you're going to have within that VPC are actually going to be private. But what we can do is that we can associate a gateway to that subnet that allows it, to that VPC that allows it communication with the internet. And then if we go to a particular subnet and use a custom route table that actually points to that gateway, will be basically telling that subnet that you are a public subnet. So the main difference between a public subnet and a private subnet is that the public subnet has a route in its routing table that points to an internet gateway associated to your VPC, which allows that subnet and the resources inside it to communicate with the internet and the internet to communicate with it if they have everything else in place. And that's the main difference. A public versus a private subnet have no difference except an additional route in the public subnet routing table that points to an internet gateway. Now, what about the private subnet? What if I want my private resources in the private subnet not to be reachable from the internet, but I want them to be able to reach out to the internet? Now, there's no way of doing this unless you use another type of gateway that we call a NAT gateway. And we basically place a NAT gateway in a public subnet, and then we go to the route table of the private subnet, and we add a route in that table that points to the NAT. And then the NAT uses the routing table of the public subnet to point to the internet gateway. And the internet gateway gets you out to the internet. Now, it's quite simple. Now, keep in mind that this is one-way communication. So the communication has to be initiated from the private subnet, and then it gets a response. It's not going to allow the other way around. So if you're sitting at home here, you cannot actually use the NAT to reach into the network. That's not possible. This path is not actually going to be supported. All right, so that's how internet gateways and NAT gateways actually work. So the internet gateways is going to allow you to create an internet gateway and then associate that internet gateway to a VPC, and then that's not enough to allow the subnets to communicate with the internet. You would still need to go to that subnet and then modify its routing table. So look at this. Here is the internet gateway. It's associated to my VPC. And then I need to go to the route table of that subnet that I want to make public. And then to the local route that it has inherited, I actually can add an additional route that points to the internet gateway ID. That internet gateway is going to have an ID. So we can actually reference that in our routing table. And so if you have an instance here, now that instance can route its traffic to the internet gateway and then out to the internet. And if that instance has a public IP address, then somebody sitting at home, well, can actually send traffic over the internet and into the VPC and then to that instance if it has a public IP address. Now, it's not only going to be a public IP address, there will be some additions to that as well that are required. But at least for now, let's think about it like that. We need an IP address for the instance if we're going to communicate with it from outside. We don't really need a public IP address if that instance is going to be communicating with the outside world, but it's not going to accept traffic coming in. All right, so it's only required if we're going to accept traffic on that instance. And on the other side, a NAT gateway is going to give those resources in the private subnet a breathe where they can actually send their traffic to the NAT gateway on the public subnet, and then the NAT gateway routes that traffic out to the internet. Right. So it may be, for example, an e-commerce website running on an instance here, which represents my web front end. And maybe this is a back end application server. And that application server wants to finalize a payment checkout. So it needs to communicate with an external banking system. It is in a private subnet. So absolutely, it doesn't have any route in its routing table that points to the internet gateway. So the only way out is that it sends its traffic to the NAT gateway ID, and the NAT gateway sends that traffic outside, communicates with the external bank, and when it completes the process, a response comes back and gets redirected to the internal application server. So that's a use case where you might actually use an architecture that looks like that. Hope it makes sense. All right. So next, if we look at use cases for those public versus private subnet. Now, if I have a data store instance, maybe a database instance or a file server or whatever it is that we are storing our data into, well, I'd probably be interested into making sure that this resides on a private subnet. Back-end instances are pretty much going to be the same. Those are the servers that are processing our business logic. I don't want them to be reachable from the public internet. If we have a web application instance, we need that to be front-facing the internet. I would be interested into making sure this is in a public subnet, except that it can actually be in a public or a private subnet. And the reason behind that is that AWS has this construct called load balancers, which we can place into a public subnet, and even our web front end servers can be in a private subnet, and still the load balancer would be able to redirect the traffic to those private subnets with no issues. So you have an option of making them public, which is quite natural. But if you also want to further protect even your front end resources, you can also place them in a private subnet and use a load balancer to hide them in the back end of your network. Cool. So next are some of the recommendations by AWS when you create subnets within your VPC. So typically you should consider creating larger subnets over smaller ones. Now I'm actually going to create a small subnet that is a /24, even though it's not preferred, but this is for demo purposes. In production environment, pretty much the production requirement is going to drive the sizing of your subnets. So it's something that you're going to discuss with your team. What size should I build my subnet? But for our demo purposes, we are actually going to use a small one. Right. The reason behind preferring larger subnets over smaller subnets is that if you have multiple workloads, placing them across multiple small subnets is going to be more complicated from a networking perspective rather than one large subnet. But on the other side, if you have isolation requirements and you want resources to be isolated in their own networks, then that's actually a reason to do the opposite of that and create more subnets that might be small or medium sized, whatever it is. Uh, but again, it's something that you have to decide depending on your production requirement, in fact. Now, it is also less likely that you run out of IP addresses. Now, remember that every time you create a network within your VPC, you actually lose 5 IP addresses. Now, this number might seem small if we are creating 3 or 4 small subnets, but if we are creating hundreds of small subnets, 5 IP addresses for each one of them is going to pose a large number of IP address waste. You also don't want to do that. All right, so looking at this slide, this is a basic subnet configuration. So what I would do is I would create a VPC, pick up whatever the CIDR block for that VPC. In our case, we're going to go for a /16 VPC. So we're going to take the whole available range, and then we're going to slice smaller pieces out of it as per our requirement. So what you can do is remember that the VPC is actually spanning multiple availability zones. So we've got an availability zone A and an availability zone B. The VPC lives across all of the availability zones within that region. So what we can do is that we can create a public subnet and a private subnet on the first availability zone, and a public subnet and a private subnet on the second availability zone. And typically, the reason why I would build an architecture like that is so that I can actually have my resources being highly available. So I can maybe have a couple of instances here with a load balancer front facing them and distributing the traffic across those two instances that we have. Again, we said that you can actually place those in private subnets as well, and still only place your load balancer in the public subnet if you so choose. But we're not going to complicate it that much. We're just going to build a simple VPC configuration. All right. Now, if you're not really sure about where to start, you typically start with one public and one private subnets, and then start increasing the number of subnets as needed. So you can actually create additional subnets at a later point, as far as your VPCs still have an available IP address range that haven't been allocated to any subnet. So looking at this, the first subnet here is 10.0.0.0/24. The second subnet here in another availability zone is going to be 10.0.1.0/24. And the third private subnet here is going to be 10.0.2.0/23 or 24 as well. And then finally, the last one is going to be 10.0.4.0/23. Right? So that's a very simple VPC. And let's actually switch to the practical part of it to actually build that together. But before going there, let me just bring in my drawing dashboard here. So here's what we're going to do to recap for what we've covered so far. So we've got a region. So this is going to be representing our AWS region. All right. And within that AWS region, let's just type a region here. Okay. This is going to be our region. And within that region, we've got multiple availability zones. So I'm going to create the availability zones a little bit curved. So I'm going to do 2 availability zones for simplicity. So that's the first one. I'm going to copy it. And I'm going to paste that and place it right here. So now we've got 2 availability zones. So again, let's just put a text around that. So this is AZ1. And another text here that says this is AZ2. Right? And then we are going to create a VPC. So the VPC, I'm going to create that as a square on top of it. So remember, a VPC is actually going to span all the availability zones that we have. So I'm going to create that one. And I'm going to place a text here that says VPC. And I'm going to point that pointer to the VPC. All right, so now you know what that is. And typically, this is going to be the availability zone, and this is going to be the other availability zone. All right, and then we are actually going to create subnets inside it. But before we do so, let's actually do the first part. Pick up which region we're going to build our VPC into, and then create the VPC. And we're not going to pick up any particular availability zones. We'll just create the VPC, and it basically stretches all those availability zones. The availability zones that we are going to use are going to be decided at a later step when we start creating subnets. So we're going to get back to that drawing again to see what's there. I'm going to bring in my console. So now you can see my console screen, and I'm actually on the main page of that console. And up to the right corner here, I'm actually in the Ireland region. You could pick up any other region that suits your requirement, depending on where you are. In my case here, I'm okay with Ireland region. If I go to the VPC section, and if you don't have it in the recently accessed services, you can always type it here. So you can just type VPC up here, and it will show up in the drop down, and then you can actually pick it up. Same thing. And I'm going to go to the Your VPCs section. And right away, as soon as I do that, you can see that there is a VPC there, and I haven't created that VPC for sure. This is a default VPC. When you subscribe to an AWS account, we create a default VPC for you by default. You can actually use it, or not. We do not recommend using it in production, only use it for learning purposes. So we're going to neglect the fact that we have a VPC here, and we're actually going to build our own VPC. So the first thing I'm going to do is to create the VPC, and I'm going to call it test-VPC. And I'm going to go for an IB version 4 CIDR block, and I'm going to pick that manually. I'm not going to use my own IPAM server or any of that. So I'm going to go for 10.0.0.0/16 as promised. I'm not going to go for IB version 6, and I'm not going to go with any fancy configuration related to the tenancy. I'm going to leave it at the default. So the first thing I'm going to do is that I'm going to create that VPC, and now it just created me a VPC in Ireland. If I go back to your VPC section, you can see now I have a test VPC in place with a CIDR IP address there. If I go back to my drawing, that part of the drawing is actually completed. All right. So the next thing that that we might be interested in doing is creating the subnets. So let's actually do that on the drawing first. So now when I create a subnet, I can let the console interface decide the subnet on my behalf, or I can actually say I want to make sure that it's actually in that particular availability zone. And that's what I'm going to do. So I'm going to create two subnets, one that is public and another one that is private in the same availability zone. So now I've got two. And similarly, one public and one private in the other availability zone. Right, so now I'm going to have four subnets. Those four subnets are going to be one public, one private, and one public, one private on the other side. So let's just put some text here. So this is going to be public subnet 1. Copy that. And I'm going to paste it in here. And I'm going to change this to be public subnet 2. And this here. And I'm going to point this here. So now you know where the pointers are actually existent. I'm going to paste in one more time, but this time this is going to be my private subnet 1. Here. And again, I'm going to copy that, paste it on the other side. And this is going to be my private subnet 2. I'm going to point that here. So now those are my four subnets. Now remember when I created my VPC, there has been a routing table that was created for me by default out of the box. Now, when I create those subnets, they're all going to inherit that routing table. And that routing table has only the local route as we mentioned on the slide. So that makes all of them actually private. Naming them public is not going to make them public. Changing the routing table will, which we are going to do at a later step. So let's just create four private subnets for now, and then later on convert them to two public and two private. So I'm going to go to the subnets board, and I'm going to create a subnet. And I'm going to pick up in which VPC they're going to live. You can see that there is a test VPC here. And it gives me a list of subnets that I can add. So I'm going to go for public subnet 1. I'm going to copy this to keep the naming convention. And here I can say no preference in which availability zone this is going to be created, or I can actually manually pick up the availability zone that I want. Now, in our architecture, we plan to use two availability zones. So I'm going to take EU West 1A, and I'm going to go for 10.0.0.0/24. So I'm going to take a small slice of the large IP address associated to my VPC. And then I'm going to add another subnet. And this time I'm going to say this is going to be public subnet 2. And I'm going to pick up another availability zone, which in that case is going to be EU West 1B. And I'm going to go for 10.0.0.0/24. Now, if I attempt to do that, that is actually going to overlap with the CIDR range that I picked up here. So I cannot use the same CIDR range for another subnet, meaning that I have to change that IP address to be .1.0 instead. So now I've got .0.0 until .0.255, and then .1.0 until .1.255. Those are two separate ranges. They're not conflicting, and they're not overlapping each other. Then I'm going to add another subnet, but this time it's not going to be public. Instead, it's going to be private. Subnet 1. I'm going to copy that. I'm going to make sure it's in the first availability zone. So now we got one public, one private in the first availability zone, at least from a naming perspective. I'm going to go 10.0.2.0, again, to avoid conflicts, /24. And then finally, I'm going to add one last subnet, which is going to be private subnet 2. And that's going to be in the second availability zone. So now I have another one public, one private subnet in the other availability zone. And this one is going to be 10.0. Last one we used is 0, 1, 2. So this is going to be 3.0/24. Now, presumably, if everything is fine, if we click Create Subnet, it just creates those 4 subnets. And if we expand this a little bit, you can see that we've got one public subnet here, one public subnet there, one private subnet here, and one private subnet there. But if you actually look in their properties section, there is something called a route table. If I click on that route table, they're all using this route table. And I didn't create that route table myself. But if I click on it, it will actually take me to the route table section. And it will filter them out and show only that one route table. So let's look at this route table and the routes inside it. This is the default one. If I click on it, and you can see it says main here. If I click on routes, it has only one route, which is a local route that allows all instances across all subnets communication with each other. Now, all of them, whether they are public or private, they're actually using that route table. They inherited that route table. So we need to change that. We need to create a separate route table so that we can distinguish public from private subnets. Now, in order to do that, the first thing I need to do is to go back to my drawing here, and I need to provide an access to the internet. So I'm going to click here and create a gateway and attach that gateway to, let's just imagine that this shape is going to represent the internet for now, just for simplicity, so that I don't have to switch between different pages. So if I want to get to the internet, I need a gateway. So we're going to create an internet gateway. So this is going to be internet gateway. And make sure that we point it here so you know what that is. Maybe drag this a little bit out. Or even connect it in another spot. Right, so that's our internet gateway. That's our exit to the internet. And then we need to go back to the route table on those subnets and actually provide them access to that internet gateway. So let's just do that. I'm going to go into the internet gateway section. Again, that's the one for the default subnet. I didn't create it. I'm going to create my own. And I'm going to call this test internet gateway dash here. And I'm going to create the internet gateway. And once it is created, I can click on its action, attach it to a VPC, and pick up my test VPC, and then go ahead and attach. right? So it's even faster than drawing it. So now this part is done. We do now have an internet gateway associated to our VPC. All right, so the first part is done. Next, we need to create a route table that points to it. So we're going to create an additional route table. There is one here created for the default network and one created by default for my test VPC. I didn't create that. It just gets created by default. So I'm going to create another one, a custom one of my own choice, and I'm going to call it test-vpc-public routing table or public RT. I'm going to associate that to my test VPC. So now we know that this route table resides in that VPC. I'm going to create that route table. Now the route table is there. Then I need to edit its routes because it also inherited the default one, but I just need to add another one that points to the internet gateway. So I'm going to edit routes, and I'm going to add that, and I'm going to say from 0.0.0.0/0, meaning any subnet that will have this route table associated to it, any IP address inside it, can actually reach the internet by going to the internet gateway that we have created earlier, the test internet gateway. Then go ahead and save the changes. Great. So now the route table is successfully created, and it has a route that points to the internet gateway for sure. It's time to associate it to those subnets that we want to make public. So I'm going to click on Subnet Association section, edit the subnet association. It gives me a list of all of them, and I only need to pick up the public subnet and the public subnet too, and leave the private ones as is. So I'm going to save the association. And now, if we go back to the subnets and filter them by our test VPC, we get only 4 subnets here. If we click on the public one and look at its route table, it has the 2 routes, the local route and the one pointing to the internet gateway. Similarly is public subnet 2. If we go to its route table, it has the 2 routes because they are associated to the same route table. But if we pick up the private subnet one and check its route table, it's associated to the default one, and that means they only have one local route. They cannot communicate with the internet. They can only communicate locally, the private subnet 1 and the private subnet 2 as well. So now we can say that, yes, we do have 2 private subnets because they don't have route in the routing table that points to the internet gateway, but we do have, but we do have, let's just draw the routing table, something like this. And again, I'm going to call for something like this. They do have now a route in the routing table that points to the internet gateway, which makes them public and makes those ones in the back here private. All right, so we've achieved it. Perfect. So now let's go back to the slide. This is what we've done. We've actually built that network, but we only added an additional gateway to it, which allows us communication to the internet. Now, how do we control traffic within that VPC? Now, if we want to control security within this VPC, then we have 2 simple methods that are free of charge from AWS that can allow us to do this. The first one is a security group. And a security group is a simple rule-based firewall that actually surrounds your instance and restricts any traffic from getting into that instance. Then you can actually go and modify it to allow that particular traffic that you want to allow. Now, in order to do that, we need to create an instance in order to be able to see how it works. So let's just go back to the interface and switch to a different service this time. This is going to be EC2 service. I'm going to click on EC2 service. And on the instances section, let's launch an instance into that VPC. And I'm going to pick up a simple Linux instance. I'm not going to go into the details of that. I'm sure you've actually seen that in other sessions. And I'm going to pick a t2.micro instance. Then I'm going to configure the instance details, making sure that I pick up my test VPC, and also making sure that I place it in a public subnet. So I'm going to pick up public subnet 1 from the list. And I may also choose to ensure that I give it a public IP address, because if I want to connect to it from the outside world, I'm pretty much going to need that. And then just go ahead and in the add storage section, I'm going to leave it at the default. I don't want to change that. I should add a tag to identify that instance easily later on, but I'm going to leave that at the default as well. No additional tags. This is the part where I actually look forward, is the security group. Whenever you create an EC2 instance, it has to be a member of at least one single security group. Now, lovely from the AWS Management Console, it detects that this instance is a Linux-based instance. So it says, well, you probably might need to allow SSH over port 22 from an IP address range of your own choice. So would you like me to create a simple security group for you? I'm going to call this wide open security group for now. And I'm going to put the same thing in the description, right? And even though this is against the best practices, I'm going to allow SSH over port 22 from any IP address. I should actually restrict that to a custom IP address range if I want to. But again, for simplicity, I'm going to pick up any IP addresses. And right away, you can see there's a warning here that says this is against the security best practices. I'm fine with that. So I'm going to review and launch the instance. And as I launch the instance, it says, would you like to choose an existing key to connect to that instance, or would you like to create a new key pair? You can actually go ahead and create a new key pair or choose an existing one if you have one in your account. I don't, so I'm going to create a new key pair, and I'm going to give it a name of test key. I'm not really going to use it to connect, but if I am, then I need to download that key, which gives me the PEM file that I can convert to a PPK, and then later on use it to connect to that instance. And then I'm going to go ahead and launch that instance. And as I do, you can now see that this instance is being created. It's currently in a pending state, and it has been created in that VPC in that public subnet 1. All right. And if I check its security group, if I go into the security section, the security group is here. If I click on it, I can later on come back to that security group and edit inbound rules. So let's say I convert that instance to a web server. Then I may need to add an additional rule that allows something like, I don't know, HTTP or HTTPS traffic, for example, and then say this is going to be also from anywhere, and then just go ahead and save that rule. So now anyone can communicate with that instance if it's a web server, of course, using HTTP or connect to it remotely using SSH. Pardon me. So now going back to the slide, we've just created a security group, and then that security group is actually surrounding our instance, and we're only allowing SSH and HTTP at the moment. Now, I can allow traffic in, and by default, a security group allows all traffic out. So every time a security group is created, it's going to block all inbound traffic, and it's going to allow all outbound traffic. In my case here, I actually went in and said, okay, I want to change the allow list from blocking all inbound traffic to allow SSH and to allow HTTP. So I've actually modified the section you see on the left side here. Now I'm allowing SSH as well as HTTP, right? I don't have to allow traffic out because it's by default going to allow all outbound traffic. Now you can use this technique between different resources within your environment. You can use one security group to protect multiple instances if you want. to say, for example, all my web front end are going to allow HTTP from anywhere, but my database is going to allow certain kind of traffic over certain kind of ports, but it's only going to be from my web front end. And so I can ensure that no direct communication comes from the evil internet into my VPC and then communicating directly with my database. This is not going to be allowed. But traffic can communicate with my web front end servers, and my web front end servers can actually talk to my back end database, allowing you to secure your private resources. All right, and that's what we call a chaining diagram or multi-layered defense, where you can create an inbound rule to the website that allows HTTPS or HTTP over port 443 from anywhere. But then for the application servers, you're going to allow HTTP traffic over port 80, but only from the web tier security group. So this is the web tier security group that is protecting the web servers. So no other traffic from any other location is allowed. This is all going to be denied. Only that kind of traffic is going to be allowed. And the same thing for the database. You're only going to allow traffic coming from the application tier, but nothing else. All right. Now, just like the security group, we have what we call a network access control list. It pretty much does the same thing, but it does this on the level of the entire subnet. So it's not going to protect a particular instance, but it's rather going to protect all the instances within that subnet. And this one has an inbound and inbound traffic control, and you can actually allow or deny. But just keep in mind that as the security group is stateful, you only need to allow traffic in, and it automatically knows how to send traffic back out. The network access control list is stateless, meaning that if you create a rule to allow certain traffic in, let's say SSH over port 22, you have to create a rule on the outbound section that allows SSH over port 22 as well. So you have to, whatever you allow in, you also have to allow that out of your network, out of your subnet. So unlike the security group, you only have to allow the traffic that you want to get in, and it automatically will be able to go out. In the network access control list section, whatever you allow into your subnet, you have to write another rule to allow it out of your subnet. Right? So stateful for the security group versus stateless for the network access control list. An instance level for the security group versus a subnet level for the network access control list. So now you pretty much understand that if I want to communicate with an instance from the outside world, I need a few things. I need that instance to be in a VPC where there's an internet gateway attached. I also need to make sure that the subnet of that instance has a route table that has a route in it that points to the internet gateway so that we can communicate back and forth between that instance and the internet. I also need to make sure that this instance has a public IP address or another construct called elastic IP address, which is a static public IP address. You can actually book that within AWS as well. So public IP address or elastic IP address, they're both going to do the same thing for you, and they're going to allow this instance to be reachable from outside. You've seen that as I created my instance, I made it, I associated a public IP address to it. And then you also need to make sure that the network access control list, as well as the security group, both of them allow the traffic in, and the network access control list allows the traffic out. Otherwise, it won't work. It's as simple as that. So these are all the requirement that needs to be in place in terms of building a VPC and actually spinning up a resource that is reachable from outside within that VPC. Now, the next level of connectivity, and to wrap this up, that you should look at in terms of what other kinds of connectivities that I may be interested into knowing about a VPC. I'm not actually going to cover that in this particular short session, which I know that I went a little bit over in terms of time. But it's important to know that you may work in a company, and that company have an on-premises data center, and they can either, from within that company, they can reach to instances running in the network over the internet if those instances are actually in a public subnet, and those instances have a public IP address, and everything else that we've explained is in place. But they might also need to not to send their traffic over the public internet, but rather send their traffic in a private, protected channel end to end. So in that case, they might need to create what we call a VPN. So to do that, you're going to need to have a router that routes your traffic from your on-premises environment to the internet, and a real IP there. We're going to call that a customer gateway. All right. So customer gateway. And you're going to need to create another type of gateways that you can attach to your VPC. We call it virtual private gateway. So just like the internet gateway, you create a virtual private gateway, attach it to the VPC, and you have your own customer gateway. You create a VPN, you pass in the customer gateway, you pass in the virtual private gateway, and then it establishes the VPN connection. Now, once you have that VPN connection in place, servers inside your network within the on-premises environment, they can now communicate with resources in the cloud using their private IP addresses. They can even talk to the private IP resources that you have in your private subnet if in their routing table you've actually added a route that allows you to do something like that. So rather than using the main, you can use a custom route table like this, saying that I'm going to allow all traffic from that particular subnet to the virtual gateway ID, just like we did with the internet gateway, except this time, this traffic is going to be back and forth between your corporate network and your network, your VPC network on AWS Cloud. And that pretty much takes us to the end of this day. You've already seen the demo throughout the explanation. I'm not gonna make it any longer on you. Thank you very much for being here. And you can actually locate me on LinkedIn profile using my name as you see it on the screen. And you can also use this email to send me any questions that you have for any of the topics that we talked about today, or any future topic that you want to learn about within AWS. With that being said, thank you very much for being here for this very short, focused session. And I'll send the microphone to Raj if he's here still.
Hey, thanks, Mohammed. It was a great session, and I really appreciate everybody joining this call. So, if you have any questions, then you can reach out to me, or you have email address of Mohammed Yusuf. So, thanks again, everyone.
Thank you very much. There will be recording for that session shared with the attendees, Raj. Am I correct?
Yes, that's correct.
All right, great. Thank you very much. That'll be very
Yeah,
helpful so that they can walk through the demo and do it themselves.
yeah, that's absolutely correct.
Right. Thank you very much, everyone. That's all about it today, and see you later. Bye bye.
Thanks, everyone. Bye bye.